My name is Savannah STOTTS, and I am a rising junior at the University of Southern California, majoring in chemical engineering. This is my final project presentation on phase field modeling of precipitation in high-temperature shape memory alloys. Before I start, I would like to acknowledge sponsors, such as the NSF, the online REU program, and TEMU High Performance Research Computing. I would also like to thank my mentor, Jean-Briac Legraveron and José Dominique, for their support. High-temperature shape memory alloys are alloys that can be deformed and returned to their original shape before deformation at temperatures above 100 degrees Celsius. Usually, they undergo a martensitic phase transformation between an austenite high-temperature phase and martensite low-temperature phase. This shouldn't be confused with phase changes between solid, liquid, and gas. These are solid phase changes. Some properties, as shown in the graph, include shape memory effects, as seen in green, which occur at low stress and changing temperatures. This is when a material is deformed to a low temperature martensite phase, and then upon heating is returned to the high temperature austenite phase, recovering its shape. Another property is superelasticity, which is shown in red. This occurs at a fixed temperature above the austenite finish temperature, shown as AF, and is an example of stress deforming the material. After removing the stress, the material returns to its original shape without heat. If this deformation was purely thermal, then it would be actuation. We have been exploring nickel-titanium hafnium because it is of interest to NASA. I have been considering a nickel-lean nickel-titanium hafnium with nickel-4 titanium-3 precipitates. It is important that it is nickel-rich because that is what causes the precipitation. Nickel-rich nickel-titanium hafnium also demonstrates superelasticity. We want to understand how precipitates affect superelasticity and actuation with regard to solid-state phase transformation and micromechanics. Phase field modeling is a framework that is able to track interfaces, which can then model microstructures. The phase field has three components: chemical, gradient, and elastic. These all contribute to the total free energy of the system, shown here. There's also use of evolution equations, such as Cahn-Hilliard, which is responsible for the concentration and models evolution in the microstructure. Alan Cahn is responsible for the orientation variance of nickel-4 titanium-3 precipitates in the matrix, shown here. The phase field variables I have been using are concentration and N1 and N2. The concentration has been important because it has ensured that the matrix stays nickel-rich in order for the precipitate to evolve. The N1 and N2 represent variance and are responsible for the orientation of the precipitates. Shown is an example of nickel-4 titanium-3 precipitates in a nickel-titanium matrix using phase field modeling. This is similar to what we would like to accomplish, but in our model we have been using nickel-titanium hafnium instead of nickel-titanium. The motivation for using a phase field is that it is costly to conduct similar investigations experimentally while controlling key microstructure parameters responsible for modifying phase transformations. It will help accomplish the goal of understanding how spacing, number of precipitates, and volume fraction influence solid phase transformations, as well as to explore the impact of key crystallographic orientations. As I mentioned earlier, we are currently exploring nickel-titanium hafnium because it is of interest to NASA. Shown is an example of NASA's interest in nickel-titanium hafnium through ball bearings. Throughout the project, I have followed a process. I started by understanding how the phase field module and MOOS worked, by working through their examples and tutorials on how to use the module and system in general. I then investigated the fundamental equations of phase field, such as Cahn-Hilliard and Alan Cahn, in order to evolve the initial working precipitate and matrix. Once the evolution, chemical, and gradient equations were implemented, I implemented components that would influence shape, location, and number of the precipitates, such as the elastic energy and seeds. There are three main components that drive nickel-4 titanium-3 precipitates in nickel-titanium hafnium: the chemical, gradient, and elastic energy. In these equations, C represents the concentration and N represents the variance. The chemical energy equation contains the equilibrium nickel concentrations of the nickel-titanium hafnium and the nickel-4 titanium-3 precipitate. The A1 through A7 are polynomial parameters. The equation is essential for creating separation between the precipitate and the matrix. The gradient energy is also known as the interfacial energy. It plays a crucial role in microstructural evolution. Elastic energy accounts for the stress and strain, such as the precipitates creating a coherency stress in the matrix due to a lattice misfit. This energy also strongly contributes to the shape of the precipitate by accounting for its long and more needle-like shape. The elastic energy relies on 4 equations. The energy equation itself, shown here as FEL, the elastic strain tensor equation directly below it, the total strain tensor equation, shown here, and the transformation strain tensor equation, shown here. These all contribute to the total energy of the model. I have been using the phase field module on Moose to model a nickel titanium hafnium matrix with an anisotropic nickel 4 titanium 3 precipitate. By varying concentration of nickel, precipitate generation has been controlled, so keeping the nickel concentration high in the initial concentration has been important for keeping the nickel titanium hafnium nickel rich. I have been using seeding, where the precipitate is pre-seeded in a location that it will evolve. This helps with controlling the location and the number of precipitates generated. As I also stated, energy and evolution equations play a role in the simulation as well. This is an example of a precipitate I was generating around halfway through the project. It was long and somewhat sharp at the ends. Some challenges have been divergence when I first ran the simulations, so by adding solver tolerance parameters, I was able to fix this. I was also receiving multiple precipitates in random locations, as seen here. After seeding them, though, I was able to control the location and number of the precipitates and was very successful. Eigenstrain implementation and gaining the proper shape were also a struggle. The eigenstrain was implemented properly by connecting it to the n variables. The shape was fixed with the addition of the elastic energy. Shown below are images of what the precipitate shape is supposed to look like. As you can see, they're long and needle-like, and this is the shape we have been going for and the orientation that is desired. Throughout the project, I have run many 2D simulations. In the beginning stages, the precipitates were showing up on separate sides of the screen. After the gradient and chemical energy were properly implemented, these problems went away due to the precipitate and matrix being properly separated and the microstructure evolving properly. At some point, when the precipitate was showing up in its hole though, it was round at the center and was showing up in random locations, as seen here in the second precipitate. After implementing the elastic energy properly though, this problem went away because the elastic energy implemented a more proper shape. Seeding helped control the location as well. So this is when elastic energy and seeding were done, the last precipitate shown here, but there was still no eigenstrain. After implementing the eigenstrain, the elasticity, and the elasticity tensor, there was proper shape and size. Here are the precipitates being generated currently. These precipitates have been generated from concentration without orientation variance, which is why there is no tilt. This lays the groundwork for the future because once variance can be properly implemented, the precipitates and matrix can be investigated further to see how spacing, number of precipitates, and volume fraction play a role in solid phase transformations, as well as to explore the impact of key crystallographic orientations. So far, I have been able to develop a nickel 4 titanium 3 precipitate that is anisotropic, has a controlled location, shape, and size. The research direction here would be to display the orientation of the variance properly, to generate the proper shape when generating multiple precipitates, and to properly implement 2 different blocks in the code based on concentration that differentiate the matrix and precipitate in order to apply a rotation matrix. That is all. Thank you so much.